Welcome to our lecture on the additive property of chi-square. Imagine you are throwing darts at a board, and we measure how far off you are from the center. The squared distance of your misses can be described by a statistical curve called the chi-square distribution. Today, we will explore a beautiful mathematical rule that makes combining independent statistical experiments incredibly easy. Now that we understand what a chi-square distribution represents, let us look at how it works when we have multiple sources of data. Suppose your friend is also throwing darts at a different board, completely independent of you. If we want to look at the total combined squared errors of both you and your friend, we do not need to invent a brand new complicated mathematical curve. Because of the additive property, the combined errors still follow the exact same type of chi-square curve. The only thing that changes is a parameter called degrees of freedom, which simply adds your number of independent throws to your friend's number of throws. This intuitive idea leads us directly to the formal definition. The additive property states that the sum of independent chi-square random variables is itself a chi-square random variable. To understand this, we recall that degrees of freedom represents the number of independent standard normal variables being squared and added together. If we have two completely independent variables, each following a chi-square distribution, their sum behaves perfectly predictably. This property is foundational in statistics because it allows us to break down large, complex tests into smaller, independent components that can be simply added together. Let us look at the exact mathematical formula for this property. If a random variable x follows a chi-square distribution with m degrees of freedom, and another independent random variable y follows a chi-square distribution with n degrees of freedom, then their sum, x plus y, follows a chi-square distribution with m plus n degrees of freedom. The key requirement here is absolute independence between x and y. If they are independent, the new combined distribution simply takes the sum of the original degrees of freedom. If either variable increases its degrees of freedom, the combined distribution shifts to reflect that larger sum. Before we move on, let us see this with a concrete example. Suppose we have two independent machines producing resistors. The squared errors of the resistance values from machine A follow a chi-square distribution with 4 degrees of freedom. The squared errors from machine B follow a chi-square distribution with 6 degrees of freedom. We want to find the distribution of the total combined error and its expected average value. We start by defining our variables. Let x represent the error from machine A and y represent the error from machine B. We are looking for the distribution of x plus y. Continuing with our machines, we apply the additive property. Because the variables are independent, we simply add their degrees of freedom together. We take the 4 degrees of freedom from the first machine and add them to the 6 degrees of freedom from the second machine. This gives us a combined chi-square distribution with 10 degrees of freedom. For any chi-square distribution, the expected average value is exactly equal to its degrees of freedom. Therefore, the expected average value of the total combined error is 10. This means if we repeated this process many times, the average total squared error would settle around 10. Now that we have used this formula, let us understand where it comes from. To prove this property mathematically, we use a tool called the moment generating function, or MGF. Think of an MGF as a unique mathematical fingerprint for a probability distribution. No two different distributions have the exact same MGF. The MGF of a standard chi-square distribution with k degrees of freedom is 1 minus 2t, all raised to the power of negative k over 2. We define the specific MGFs for our two independent variables, x and y, by replacing k with their respective degrees of freedom, m and n. Moving forward with our derivation, we use a fundamental rule of probability. The moment generating function of the sum of two independent random variables is equal to the product of their individual MGFs. Let z be our new combined variable. x plus y. Because x and y are independent, we can simply multiply their individual fingerprints together to find the fingerprint of their sum. This multiplication step is the crucial mathematical engine that makes the additive property work. We substitute the actual formulas into this equation, setting up an algebraic multiplication of two terms with the exact same base. Concluding our proof, we apply the rules of algebra. When you multiply two terms that have the exact same base, you simply add their exponents together. By adding the exponents, we get a new exponent containing m plus n. Look closely at this final result. It has the exact same mathematical structure as the generic chi-square fingerprint we started with. But the degrees of freedom parameter is now m plus n. Because this MGF perfectly matches the fingerprint of a chi-square distribution with m plus n degrees of freedom, we have successfully proven that the sum must follow that exact distribution. So, we have proven that the additive property holds. This brings us to a visual representation of what we just derived. Here we see three probability density curves. The blue curve represents our first independent source of error, x, with 3 degrees of freedom. The green curve represents the second source, y, with 5 degrees of freedom. When these two independent sources are combined, the resulting red curve is still a perfect chi-square distribution. Notice how the peak of the red curve shifts to the right, reflecting the sum of the degrees of freedom, which is 8. The shape remains consistent, just stretched further along the axis. This visual understanding leads us to one of the most powerful real-world uses of the additive property, goodness of fit tests. When analyzing contingency tables, statisticians calculate a small chi-square error value for every single cell in a grid. Each cell's value measures how far the actual count is from what we would expect. Because of the additive property, we do not have to analyze each cell in isolation. If the data in each cell represents an independent source of variation, we can simply add up the chi-square values from every single cell to get one massive overall chi-square statistic for the entire table. Let us formalize this application with an equation. The total overall chi-square statistic is the direct sum of the individual contributions from each independent component. In this formula, C sub I represents the chi-square error contribution of the ith component, such as a single cell in a table or a single face of a die. The additive property guarantees that this simple addition is mathematically valid. By adding them up, we capture the total deviation in one single equation. As the individual errors increase, the total chi-square statistic grows, indicating a larger overall deviation from our expected values. Let us apply this formula to a real scenario. A researcher is testing a new 6-sided die to see if it is fair. They roll the die many times and calculate a chi-square error contribution for each of the 6 faces based on how often that face appeared compared to the expected number of times. The individual chi-square contributions for faces 1 through 6 are calculated as 0.5, 1.2, 0.3, 2.0, 0.8, and 1.2 respectively. Assuming these contributions act as independent components, we need to find the overall chi-square statistic for the entire die. Continuing with our die experiment, we use the additive property to combine the individual error contributions. We substitute the specific numerical values calculated for each face of the die into our sum equation. We simply add 0.5, 1.2, 0.3, 2.0, 0.8, and 1.2. The final overall chi-square statistic for the die is 6.0. The researcher would then take this single number and compare it against a standard chi-square distribution table to determine if the die is truly fair or biased. This single number makes the final decision-making process incredibly simple and clear. We have covered a lot of ground today, so let us review our key takeaways. The additive property of the chi-square distribution is a simple but powerful rule. When you add independent chi-square variables together, the result is a new chi-square variable, whose degrees of freedom is the sum of the original degrees of freedom. We proved this mathematically by showing that their moment-generating functions multiply together perfectly. Finally, we saw how this property is the invisible glue holding applied statistics together, allowing us to evaluate complex tables of data with a single unified statistic. You now have a solid understanding of this foundational concept.